Today we are going to be continuing Chapter 5, Section 5.2, Electron Arrangement in Atoms. This is our second period, so please watch this recorded lesson before the second live session. We are in Week 10, Period 2. The resources we are going to use are our textbook, pages 134 to 137, PowerPoint slides and recorded lessons, a video related to the concept, and the MS Teams assignment. Your guide for this week is, first of all, you're going to head to the Teams, go to Files, Collateral Material, and download Week 10. Please read the textbook, pages 134 to 136, and go over the PowerPoint slides prior to attending the live session. So watch the recorded lesson, attend the live session, ask questions to assure understanding, and then solve the assignment. Do not solve the assignment unless you are 100% sure you understand the lesson. This week's objective is we are going to list the 3 rules for writing electron configurations. We are going to apply the 3 rules in writing electron configurations in the box form, because in the first period, we already know how to write electron configurations now, right? And we're going to conclude writing electron configurations in letter form. Our keywords for Week 10, Period 2 are electron configuration, AUFABU principle, Hund's rule, and Pauli exclusion principle. So to start our lesson, I need you to open your textbook, page 134, read the first paragraph. What I need you to do is identify the 3 rules for electron configuration and highlight the definition of electron configuration. I'll give you a 2-minute timer to get done with it. Actually, 1 minute and 30 seconds are enough, right? So let's read it together. What are the 3 rules for writing electron configurations of elements? In atoms, electrons and the nucleus interact to make the most stable arrangement possible. The way in which electrons are arranged in various orbitals around the nuclei of an atom are called electron configurations. 3 rules, the AUFABU principle, the Pauli exclusion principle, and Hund's rule, tell you how to find the electron configuration of atoms. So what we technically identified from reading is what I need you to discuss. I'm going to give you some time to read it on your own again. Okay, so what we concluded from reading is the electron configuration definition, the way in which electrons are arranged in various orbitals around the nuclei of an atom. We also found the 3 rules for writing electron configurations, the AUFABU principle, the Pauli exclusion principle, and Hund's rule. Okay, so now we're going to learn how to write the orbital diagram, which needs some rules. So from the paragraph we read earlier, what do you think are the 3 rules? I'm going to give you 30 seconds to answer this question. What are the 3 rules for writing electron configuration of elements, of electrons? So we want to write the electron configurations, and we have 3 rules. Did you get the answer yet? Okay, so we have the AUFABU principle, the Pauli exclusion principle, and Hund's rule. These rules tell us how to find the electron configurations of atoms. Now, we will be watching a short video, and I need you to conclude the 3 principles. Tell me, what did you understand about the three principles?
Electron configuration refers to the arrangement of the electrons in an atom into orbitals. To determine the electron configuration of an atom with multiple electrons, we follow something called the AUFABU principle. AUFABU is a German word that means to build up, and that's what you do in this process. You build up the electron configuration from the bottom up in this diagram of orbitals. Electrons seek the lowest energy state, starting with the 1s orbital. We use arrows to represent electrons, and the direction they're pointing shows the direction of their spin. According to the Pauli exclusion principle, each orbital holds a maximum of 2 electrons with opposite spins. So there's a maximum of 2 electrons in the 1s orbital. If the atom has more than 2 electrons, they start filling in the subsequent higher energy orbitals. Let's see some examples. Hydrogen has 1 electron, so it goes into the 1s orbital. We write the electron configuration as 1s1. The first number shows the energy level, and the exponent on s shows the number of electrons in the s orbital. Helium has 2 electrons, so those 2 electrons both go in the 1s orbital, with opposite spins. The electron configuration is written as 1s2. Lithium has 3 electrons, so we know it will start to fill a higher orbital, since the 1s orbital can only hold 2 electrons. We write this as 1s2, 2s1. Again, remember that the large numbers represent the energy levels of the orbitals, and the superscripts represent the number of electrons in that orbital. Beryllium has 4 electrons. We fill the diagram from the bottom up. The electron configuration is 1s2, 2s2. Next comes boron with 5 electrons. We're now starting to fill in the 2p subshell. P subshells have 3 orbitals, px, py, and pz, which can each hold 2 electrons, for a total of 6 electrons. We put the first electron in 2px. The electron configuration of boron is written as 1s2, 2s2, 2p1. Carbon has 6 electrons. Where does that second electron go in the p orbitals? According to Hund's rule, every orbital in a subshell gets 1 electron before any orbitals get 2 electrons, and each of the single electrons have parallel spin. So, we put the next electron in 2py, with an up arrow to show it has the same spin as the electron in the 2px orbital. After the second energy level, you really have to pay attention to the energy level diagram. For instance, notice that the 4s orbital has lower energy than the 3d orbital, so you should fill the 4s orbital first. But these 2 orbitals are so close in energy that for a few elements, electrons go into the 3d orbital first. For example, in chromium, the electron configuration ends in 3d5, 4s1 instead of 3d4, 4s2. Similarly, copper's electron configuration ends with 3d10, 4s1 rather than 3d9, 4s2. The rationale for these exceptions to the AUFABU principle is that half-filled or completely filled subshells are particularly stable arrangements of electrons. In another video, we will discuss some tips and tricks to make...
Okay, I hope we had a glimpse or a short idea of each of the 3 principles: AUFABU, Pauli exclusion, and Hund's rule. Let's start with AUFABU principle. Consider the diagram we have here. So when adding electrons, according to AUFABU's principle, we need to add from the bottom to the top. That is from the lowest energy level to the highest energy level. So the first electron has to go here. Now, where's the second electron going to go? Should it stay in the 1s or should we put it here? Well, based on Aufbau's principles, we need to fill the lowest energy levels first, which means it will not go into here, it will go here. So we're going to put the second electron also in the 1s. Now the third electron, because we already filled this s energy level, is going to go into the 2s. And the fourth isn't going to go to 2p yet, because like we said, we should fill the lowest energy levels first. So we will have it here as well, before 2p, because 2s is there. So technically, that's the basic idea for Aufbau's principle. Simply, for each new electron, make sure to add the lowest energy level first before you add up. So according to Aufbau's principle, this is simply a summary of Aufbau's principle to tell us the main points. Electrons occupy the lowest energy levels first, and each box represents an atomic orbital. Can you see these boxes? All these boxes represent what? An atomic orbital. And each atomic orbital carries maximum 2 electrons. So each orbital carries 2 electrons. The Aufbau diagram shows the relative energy levels of various atomic orbitals. We can see here that the energy from top to bottom is increasing. So the lowest energy levels are in the 1s, and then they go increasing until the 6p with the highest energy level in this diagram. The next principle we get into is the Pauli exclusion principle, which states that an atomic orbital may describe at most 2 electrons, just like I told you here. These boxes represent atomic orbitals, and each orbital contains 2 electrons only. So this is our orbital, 1 electron, 2 electrons. Okay? And keep in mind, each orbital holds each orbital holds 2 electrons that must have opposite spins. Opposite spins that should be paired. Did you notice when we were putting the arrows, one is up, one is down? So, for example, if we have this electron configuration and this electron configuration, which one do you think is correct? Think about it. Well, definitely this one is correct because they have opposite spins in opposite directions. But did you notice this one? Both spins are in the same direction. Okay, but what is the spin we speak of? Well, the word itself speaks for itself, right? Isn't it clear? A spin is a quantum mechanical property of electrons and may be thought of as clockwise or anti-clockwise or counterclockwise. Okay, so how do we represent a spin? Simply the direction of the arrow represents a spin, and the arrow itself represents an electron. That's why we said each box is an orbital, and each orbital carries a maximum of 2 electrons with opposite spins. So like we discussed in Aufbau's and Pauli exclusion principles, this is how we write orbitals with paired electrons. Here is an example. Now, I'm going to give you a few seconds, 45 seconds, to define a spin. Tell me, what do you think a spin means? We just discussed it, right? Did we get it? So 10 more seconds, 8, okay, time is ticking. I need to see these questions on your copybook. So copy them into notes as you're gonna need them to study. So a spin is a quantum mechanical property of electrons that may be thought of as clockwise or anti-clockwise. So the arrow is up or the arrow is down. These arrows represent the direction. This complete arrow, not the direction, represents an electron, and this represents an atomic orbital. So each box is an atomic orbital. The direction of the arrow indicates the direction of the spin, and an arrow itself represents an electron. Now, our last question for now, I need you to fill these blanks based on what you understood from Pauli's exclusion principle. According to what principle, an atomic orbital may describe at most how many electrons? To occupy the same orbital, 2 electrons must have how many spins? What do you think? Okay, time is up. According to the Pauli exclusion principle, an atomic orbital may describe at most 2 electrons. By the same orbital, 2 electrons must have opposite spins. Now, our last question for now is, how many electrons can an orbital carry according to Pauli's exclusion principle? A very easy question. Definitely 2, right? Of opposite spins. Now, the last one. Hund's rule states that 1 electron must be present before pairing in each orbital. So according to Hund's rule, electrons occupy orbitals of the same energy in the way that makes the number of electrons with the same spin direction as large as possible. Let's raise it into words to make it simpler. Hund's rule. Simply says 1 electron must be present in each orbital before pairing. So an analogy for this is the empty bus rule. Whenever you go to a bus, this rule says a student So the empty bus rule states that a student must sit in an empty seat alone before sitting with another student. This is exactly the Hund's rule. Hund's rule indicates that electrons occupy orbitals of the same energy in a way that makes, this is the most important statement, in a way that makes the number of electrons with the same spin as large as possible. For example, if I have here 1, 2, 3, 4, 5, let's make them smaller. One, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So we have here 1s, 2s, 2p1, 2p2, 2p3, 1s, 2s, 2p1, 2p2, and 2p3. Let's see, which one is correct? Tell me. Or what do you think is the correct option? Well, the second line, based on Hund's rule, is incorrect because this electron was paired before making the electrons with the same spin as large as possible. Can you see here? I can have this here. Same electrons with the same spin as large as possible. So it should be here. So this one is the correct example. Because I cannot pair an electron before filling all the same spin identically. Did you get the point? Let's take a look at this oxygen atom. How many electrons are in an oxygen atom? Well, for the periodic table, we have 8, right? And remember, the subscripts or the superscripts in an electron configuration represent the number of electrons. So 4 plus 2 plus 2 tells me that I have 8 electrons for oxygen. Okay, so first, let's look at the 1s orbital. It has 2 electrons of opposite spins. The 2s, also 2 electrons of the opposite spin. Now look at the important part here. The 2p orbital has 4, right? 4 electrons. We can see that each 2p orbital has an electron. Here, there is 1, 2, 3. And now the remaining pair, because we have no more p's, we pair it now in opposite direction. I hope this demonstration was clear. What we are going to do now is practice some questions to assure our understanding. So let's see our first example. Our example says, what is the electron configuration of phosphorus? This is what we need to find. We need to write this, okay? Okay, so we need to find the atomic number of phosphorus, the electron configuration, and they gave us the atomic number, which is 15. We'll first go to the periodic table to write the electron configuration to make it easier for us to draw the dot diagram or the arrow diagram, box, let's say. Where is phosphorus? Phosphorus is here. Yalla, let's write the electron configuration, like we practiced that last class. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And then 3s1, 3s2, 3p1, 3p2, 3p3. So what we have is 1s2, here's 1, 2, 2s2, and then 2p6, sorry, and then 3s2 and 3p3. This is the electron configuration for phosphorus. Okay, now let's try to write the block diagram. What we have is, we have to fill the s orbitals first, and then move on to the p. Okay, can you fill it on your own? What do you think? Do you think you can do it? Is it easy? Let's see. Our electron configuration was 1s squared, 2s2, 2p6, 3s2, and 3p3. Right? So how will we fill it? First, we have 1s2. So this is 1s, 2s, 2p1, 2p2, 2p3, 3s1, 3p1, 3p2, 3p3. Okay, so the 1s2 2 electrons in the first s orbital, 2 electrons in the second s orbital, definitely opposite spins, and then we have 2p6, so we have 6 electrons. We have to fill the maximum in the same direction right first, right? So 1, 2, 3, and then we'll fill again in the opposite direction, 4, 5, 6. And then 3s1 has 2 electrons, so opposite spins, and the p has 3 electrons, so fill up the maximum with the same direction. So this is technically our electron configuration for phosphorus. Now when it comes to beryllium, can you do it on your own? I'm going to give you a timer so you can do it on your own. What do you think? You got the answer yet? I'm going to give you the periodic table to make it easier. Although you should have your periodic table by now. Locate beryllium. Let's see how much time is left. 20 seconds. Okay, so let's try writing the electron configuration first and then find the box electron configuration. Let's see. Beryllium is here, so 1s1, 1s2. So my first is 1s2. And then 2s1, 2s2. So it's 2s2. This is the electron configuration for beryllium. And then let's do the boxes. I have 1s and another 2s. How many electrons? 2 opposite spins. How many electrons? 2 of opposite spins. So this is the electron configuration for beryllium. And now this is our last question. What is the correct electron configuration of a sulfur atom? I'm going to keep it open for you. As soon as you are done with watching the video, this is the first thing I'm going to ask for in our next live session. And please pay attention to these definitions as they are extremely important. I hope everything is clear. Please watch this recorded lesson before attending the second live session of week 10. Thank you and have a good day.